Hey everybody, I'm back. I got Joseph. Obviously, it's not your real name. Hmmph. Hmmph. How do you want to pronounce it? I'm going to call you Joe, by the way. But what, Joseph Hmmph?
You can just leave that out. I mean,
All right,
it
it's going
works.
to call you Joe. Um, I guess we're going to have this informal debate or discussion on 1 = 0.99 repeating if it's true or false. Frank Dunley in live chess, that's non-standard analysis. Actually, even in non-standard analysis, I maintain that this is true, with many different ways to show. And I think, Joseph, you disagree with that?
Yeah.
Okay. Why don't you start? By the way, have you seen the videos on this? Have you seen what I've written on some of these videos?
What, on the subject of point nine repeating?
Yeah, I've actually written long, intricate comments on YouTube videos, like My
No,
Heart's video and Singing Bananas. Okay.
I I think I've seen Vihart's video before. She's the person that does like videos in which she writes stuff down on paper and draws shit.
Yeah,
Yeah.
she calls herself a music mathematician or something. I remember something. Very, very talented. Yes.
I wasn't sure if you were wanting to start out with like going ahead and describing why you think it's the case, or if you would like me to basically provide why I don't think it's the case that one equals
Sure.
one.
Either way, I'll just give a quick thing. 1 = 0.9 repeating is by definitionally true, as well as um, true by many different methods of algebra, calculus, geometric progression. The definition of a limit of a sequence is that anything that the number converges upon is the limit of that sequence. So 0.99 repeating converges upon 1, therefore the limit is 1, therefore the limit of the sequence is 1. It's no different than saying 1/2 is 0.5. That's a terminating decimal. So 1/2 equals 0.5. But sometimes you can't have a terminating decimal. You have even in long division, you'll take one number, you put another number, you keep going forever. That's why it's called an infinite decimal expansion. 1/3 is equal to 0.33 repeating ad infinitum. And 1/3 times 3 is 1, and 0.33 repeating times 3 is 0.9 repeating. They have to be the same thing in order to have equalities. If they weren't the same, you wouldn't have an equality. And also, there's many other reasons. I'm going to let you jump into there, and then as we go in, I'll show you some mathematical reasons why this would be the case, though.
Yeah, I guess I can address the whole limit thing since that's what you brought up in a minute. I guess I'll lay out why I don't think it's a number, and then we'll go into. So my position is that point nine repeating is not even a number. So my position isn't simply that there exists some number point nine repeating that's some separate number from one. That seems silly to me. What I am claiming is that point nine repeating doesn't qualify as a number because for it to be a number, numbers have to represent quantities, or they have to basically represent what would happen if they were to represent quantities. Um, and with that in mind, like for something to be a quantity, you have to have that quantity be something that you can arrive at from other quantities, and point nine repeating doesn't qualify.
Okay, so you can actually construct. You said it wasn't a number. Well, I can actually show that it is a number. You can actually construct 0.99 repeating using what's called Dedekind cuts or by a Cauchy sequence. These are valid methods by which you actually will create a number. So it can
Well,
actually be mathematically constructed and shown to be an actual number.
no, you can construct it by using infinities, or basically this idea of what happens when I approach this idea of infinitesimal.
Well,
So,
no, there's no such thing as an infinitesimal in the reals except for 0.
sorry, not infinitesimal, infinite.
Okay.
But I guess my problem is like even if you take into account like for example with limits, right? If I try to derive this idea of, from limits, what you're doing is the limit is describing this idea as to what happens as you approach this thing, but the fact that you're implementing this idea of approach means that you're no longer actually working with a description of a real number. You're just describing what happens when you get very close to such a thing.
0.99, okay, 0.99 repeating, though, is on the real number line. It exists on the real number line.
Okay, well, how do you derive it from other quantities, I guess would be my question.
Well, you would actually, there's a couple of different ways you would construct it, but you have to first realize, again, if 0.9998 or something, right, a terminating number, that's on the number line. 1 is on the number line. Anything between that is on the number line.
Right, but 0.999 repeating is not between that. Like,
well, actually, it's not between it. It's actually on 1. It is exactly the same exact space as 1 is located. They're mathematically equivalent. They're just numerical representations that differ. 1 is a symbol. It's a numeral. It represents a concept. It represents a point on the number line that we are going to attribute to 1. 0.99 repeating is just another way of showing that exact same point. It's just a different way of representing it, no different than saying 1/2 or 0.5. One's fractional, one's decimal. 0.99 repeating is just a numeral that represents 1. That's all it means. It's a real number that exists on the real number line.
Okay, yeah, but okay. Again, I would like to see how you actually are deriving the number from.
I'm putting the live chat first, and I'll put it in here. This is you have the group chat
for the Hangout. Okay, there.
Okay, what that is? Can you see that in the group chat that I just put in the live chat?
Yeah, I see. You say equal to the limit as k approaches infinity for 9 over 10 to the power of n.
Yes, and then n equals 1 to k, and being natural numbers. So what that's saying is that's the definition of a limit of a sequence. So that sequence is defined by that calculus representation. Okay, that is by, I mean, literally, if you go to Wikipedia, that even says this is the definition by limit of a sequence. It does it for 0.33, but the principle is the same. So that's actually the mathematical construct for 0.9 repeating. Now,
yeah, but you're only describing what happens as you approach that number going to infinity.
No, and that's not how summation works. No, that's not how summation works. The summation tells you what's happening at that point. We get there by taking a progressively smaller division. Like, for example, if we do a derivative on a curve, we're taking the secant line at some 2 points, and then we're taking the secant line at a closer point, and then a closer point, and we're getting closer to 0. At that point of 0, we are taking the exact tangent line of the point on that function. Same thing we're doing here. We're actually taking it at that point. So it's not just getting closer, it's saying what happens at that point. If, for example, if I have 1/2 plus 1/4 plus 1/8 plus 1/16, you add all those together, you get 1.
Well, the foundation of being able to understand derivatives to begin with is this idea that you can't have them be at the same point, otherwise you don't derive the line, right? You fuck up the line that you're trying to derive to be able to give you that derivative, right? And so if they're quote unquote on the exact same point, then you no longer actually have developed a means by which you have that derivative.
That's why the limit is equal to the thing where the convergence.
Right, but at that point, then you're just describing what happens as you approach that thing. And to be fair, if you could derive the limit to be close or closer, depending on how precise you need to have this idea of a change between two different moments. But like, the point is, you can never arrive at what exactly that amount of changes between those two moments, and it's only a matter of how precise you actually develop into that limit as you approach whatever you're approaching.
Well, I can say that's completely wrong, for the fact that when you take a derivative of a function using first principles, which I just did a presentation on the Great Debate Community channel the other day, you can actually see that using first principles, by taking secant lines and getting closer and closer, it'll actually give you the tangent line at a specific point, which means that it actually gives you it at that point, right? I want the slope. I want the slope of the tangent line at a certain point. I can use limits to get me that tangent line slope, which means it's exact.
Well, I never disagreed with that. I'm just saying.
Same principle here.
Sorry?
Same principle here. I'm using limits to take the infinite summation of what it converges upon. And by definition, what it converges upon is the limit of the sequence, which means that 0.999 is defined by a limit of a sequence to be 1. And also, let me show you something real quick. That thing I just put in the group chat, this is also Oops, that's not the same thing. Let me get it. One check.
Looks like he posted the same thing again.
Yeah, no, I know I copied it wrong. So let me post it in the live chat first. Okay, see this right here? These look identical. That actually is the sequence for 1 by definition. 0.999 and 1 use the same sequence, the same limits. They're
right,
both.
but when you end up getting that number back, right, I would argue that you can't say that you would get the number 0.999 repeating back, right? Like, yes, conceptually, as you approach 1, right, you end up having the idea of 9s repeating infinitely, right? But that doesn't mean that you've ever arrived at a thing called 0.9 repeating forever.
Well, first of all, sequences are not biconditional. If I have a summation, a 0.1, 1/2 or 1/4 all the way to 1, right? I can't just say I want to take that 1. I'm going to, make a new sequence out of it. You don't know what sequence got you there. That's true, right? I could break down 1 into 1/2, 1/4, whatever, and I can make that. I can formulate that, but there could have been a different sequence that got to 1. But it never claims to be biconditional. But the formula that limit as k goes to infinity, summation n 9 over 10 to the n, that is the same formula for both 1 and 999, which means they have to be equal. See, the problem I think you're having is a conceptual one and a mathematical one, such that these things have to work out. Mathematics has to have a consistency to it. If you say 0.99 repeating is not the same as 1, you're breaking all of calculus for the most part. But it's also saying what number.
Well, no, I could just state that what you're approaching is 1, and then say that it's essentially, if you keep infinitesimally getting out a bunch of 9s after the decimal, right, what you can conclude is that you're approaching 1, but there's no such thing as this idea of 0.9 repeating that exists as an actual number.
But it is an actual number. You can't just hand wave that away and say it's not a number.
Well, of course I can, because the only way that you're able to even remotely conceptualize this thing is through infinities.
Not necessarily. I mean, if I think it's more conceptual with a 0.33, because you can just divide 3 into 1.0, right? And you just keep doing that over and over again. You can do that ad infinitum, but that still generates a number, 0.333333 ... right?
Right, but we understand that 1 divided by 3 is a real number.
Well, yeah, but
you can derive that. That doesn't break the rule that I was setting to begin with. Was this idea that you can derive that by you can essentially get there, right? From other quantities, right? Because.
But you're just saying it's not a real number. I can construct it.
I'm not just saying that. I'm saying it doesn't qualify because you can't get there by using other quantities, right?
You can construct it. Wait, Joseph. You can construct it using a Cauchy sequence. It's not easy, and I couldn't do it off the top of my head, but I've done it before with a mathematician, so I know it can be done. If you look up Cauchy, that's a way to do mathematical construction of how to make a real number, and by using a Cauchy sequence, you can make a real number, and it's 0.99 repeating. So mathematically, it can be proven that it is a real number. Well, and it's also
if you would like to show that in chat and explain to everyone how that works, we can. But I thought we were discussing limits, how you get there through limits. Do you hold that limits is a fair way to say that 0.9 repeating exists as a number?
You don't even have to take a limit for it. 0.99 repeating is a number without limits. 0.99 repeating is the number. It is the actual number that's constructed after you take the limit.
I would say that you've constructed 1. You basically are saying I'm approaching 1. You're not approaching 0.999999.
But that's not what it means. That's, I think, your conceptual error. 0.99 repeating does not mean you're approaching 1. That means it's at 1.
Sorry? Say that one more time?
0.99 repeating does not mean you're approaching 1. It means you're at 1.
No. I said that the limit is essentially defining the concept that the number you're approaching is 1, not that 0.999 repeating is 1. I don't even consider it a number.
but we can't construct it. Again, it's a little more complicated. I don't remember how to do Cauchy very well. If we have a
I know,
mathematician.
but you're arguing that it is a number based upon limits, and
No, I'm arguing a number. I'm arguing it's a number by the fact of how we can do construction in mathematics, how we actually make numbers to be existing. If you can construct a number, it's a real number. That's just mathematics.
wait, if you can construct a number, it's a number.
Yes, for example, like 0.00 ... people bring up, that cannot be constructed, right? It's non-constructible. It's not a real number because you can never get it to be constructed by a Cauchy sequence. For example, here, if I have 1 minus 0.99 repeating, what do you get in your view?
Sorry, say that one more time.
What is 1 minus 0.999 repeating?
0.999 repeating? It doesn't make any sense to me because I don't think that 0.99 repeating is a number.
Well, let's for arguendo say it's a number. If I want to subtract 0.99 repeating from 1, how would you do it?
It would end up with 0, but again, I don't think it's a number.
Right, you would end up with 0. But 0.99 repeating, again, just thinking of it as a numeral. I mean, it just represents 1. That's all it does. It represents 1. No different than 1/2 represents 0.5.
Okay, well, I can do that, but then you're sort of breaking the principle as to what people mean when they say 0.999 repeating. I mean, I can say right that 1. Let's just conceptualize it as like some other symbol, right? And that's 1. Sure, I can do that, but now we haven't really moved the conversation forward because what you're trying to say is this conceptualization of what happens as you approach infinity to arrive at this thing called 0.9 repeating.
Do you think 0.33 repeating? Do you think 0.33 repeating is a real number?
Yeah, well, yes, but like I said, I mean,
wait. So wait, 0.333 repeating is a real number. If that's a real number, times it by 3, what do you get?
You take 0.3 repeating and times it by 3, you just get 1.
No. Well, you do, but I mean, what actually do you get? But what actually? But what do you get? You actually get 0.99 repeating.
No.
0.333 repeating plus 0.33 repeating is 0.66 repeating. 0.666 repeating plus 0.333 repeating is 0.99 repeating. Yes, it is.
Well,
so 0.3 repeating times 3 is 0.99 repeating, which is equal to 1.
No. I mean, like,
yeah, so yes. What do you mean, no?
Well, I'm just curious. You're taking. I mean, you can't multiply a number that goes on forever by a number, right?
Sure you can.
Well, okay. Where are you going to start in your multiplication of that?
Start at the beginning. Euler himself did a proof at that. He proved that
at the beginning of infinite.
Hang on, Euler himself in his book, one of his books called, I think it was the Elements of Algebra, I believe. He actually demonstrated that 9.999 repeating was equal to 10 using similar things like that. Using
right, but I'm asking you how you end up essentially multiplying 3 into an infinite assortment.
Because 3 times 3 is 0.9. 0.03 times 0.03 is 0.09. You just
3 times 3 is 9, not 0.9. And when you multiply, that still doesn't answer the question. If you have an infinite number of repeating 3s and you end up multiplying,
add those together.
Sorry?
I put it in the group chat here. Add those 2 together. What do you get? And I'll put it in the live chat so they know what we're doing here.
1/6.
No, in decimal notation.
Huh?
In decimal
sorry, 2/6. 2/3. What the hell's wrong with my brain?
In decimal notation, what are those combined to? 0.666 ... Right? You put them over each other, they're going to add in the tens place, the hundred place, the thousand place, on infinitum. So it's 0.666 ... Right?
Yeah, sure.
Okay.
Okay. What about
so now I have 0.666 ... Now I add another 0.333 to it. What do I get?
We get the bunch
0.999 repeating.
Right, but I'm not saying well, I would say what you get is 1, and you shouldn't represent it as 0.9 repeating.
But that's the whole point. Is 0.9 repeating is 1. That's the whole argument. Yes, like I know the proof. I haven't got that far with them yet. I understand the proof for this. I know every proof there is on this particular topic, Nestle. But thank you. But if he doesn't understand, I'm having so many proofs because he's not accepting that it's a real number first.
Well, I guess my question is, so the way I would conceptualize adding 0.3 repeating forever plus 0.3 repeating forever is to take it in fractions and then add those things together. And then if you'd like, you could actually take the division and say, this is what happens. I mean, in a sense, I would reject that, the idea of it. Well, I guess okay. I won't say that. But
one third is 1/3 is equal to 0.33 repeating. You agreed with that, right?
Yeah.
Okay. On the left-hand side, 1/3, if I had 3 of those, I end up with 1. 1/3 plus 1/3 plus 1/3 is 1. On the right-hand side, if I had 0.33 repeating plus 0.33 repeating plus 0.33 repeating, as I did in the group chat, you get 0.99 repeating. The left-hand side has 1. The right-hand side has 0.99 repeating. They're the same number.
Right, but you're applying the same concept over and over to the fact that because I was previously able to add these numbers up, and you're conceptualizing it as like, because I have 0.3 repeating and I'm able to add 0.3 repeating to it, what I'm conceptually doing is adding up those infinitesimal amounts into each other. But I'm saying that doesn't make sense. What you're really doing is you're taking it back into fraction form, adding those fractions, and then seeing what you get as a result.
First of all, there's no infinitesimals being utilized here. None of these equations use infinitesimals, so I don't know why you keep using the word infinitesimals.
If I use the word infinitesimal again, that's my bad.
1/3 is a discrete amount. It's one. If I have a pie and I have 1/3 of it, I'm getting a discrete amount, right? And I can represent that in a fractional notation, meaning 1/3, or I could say in decimal form, it's represented by the symbol 0.33 ... Those mean the exact same thing. One's just a decimal way of explaining the other one.
Sure, but you're still. I guess my question is, you don't actually add those numbers together by taking each and every one of those 3's and adding it to every one of those other 3's to get the 0.6 repeating, right?
Yeah, you do. You can do that. Absolutely, you can do that. There's nothing.
No, you can't do that. Okay. Again, back to the original problem.
Wait. 1/3 fraction plus 1/3 fraction is 2/3. 0.33 ... plus 0.33 ... is 0.66 ... 0.66.
No. I'm saying if you're to add them together, you have to start at some number, like, well,
no, you don't.
Not number, but decimal in there, right? Well, that's how you.
3 plus 3 is so 0.3 plus 0.3.
Yeah, but my question is, which one of those are you starting at? Well, the answer is you're starting at.
You do it all at once. No, you just add them all at once. You don't have to sit there and go, okay, I'm going to do the tens place, the 100 place. That's how you would break it down. But all I can look at that and go is 0.33 ... plus 0.33 ... Yeah, it's 0.66 ... I can do that in my head. There, I did an infinite sequence in my head.
Yeah, but just saying that, well, I can just add them all at once doesn't really answer to you having actually added them, right?
You did actually add them. I don't know why you keep saying I didn't add them. I added them. Here, look, Joseph, again.
Because you have this infinite sequence. To add numbers, you actually have to take each of those decimals.
No, you do not when you do an infinite sequence. That's exactly why we developed infinite sequences and summations. So you don't have to do everything by hand like that. That's the whole reason why they have a summation when you're taking it to infinity. But maybe this might be you get around your block. You've agreed that 1/3 equals 0.33 repeating, right? You've agreed with that. So I have a slice of pie that's 1/3 and it's equal to 0.33 repeating, right? How is that any different than saying 1 equals 0.99 repeating? If you're accepting that 0.33 repeating is equal to a finite amount, 1/3, why can't you accept the 0.99 repeating is equal to a finite amount, meaning 1?
Well, because again, there's a difference between them. In one case, you're able to get there from other quantities, and in the other case, you can only arrive there through essentially taking limits, as you were earlier, or by doing this notion of, well, I can just add up infinitely repeating numbers. Like,
Okay, let me ask you this: is a pi terminate? Does pi terminate, or is it infinitely expanded?
it infinitely expands.
Okay, so it infinitely expands. I could work with pi. Pi times 2 is 2 pi. Pi plus pi. I can add that together. 3.1 for 1 plus 3.1 for 1, right? It'd be 6.2, whatever, right? I don't have to do that in my head. I can just say 2 pi. There, I've added 2 pi together.
If I'm not, pi is irrational, right?
Pi is irrational, sure.
Yeah. Uh,
Yeah. It goes
again,
on forever.
again, the conception. I would just argue that the way you're actually adding them together is through the rules of irrational numbers, right? Like,
What are the rules of irrational numbers to add them together? Do you know
fuck
what
them.
an irrational number means?
Yeah, it's one that's not a fraction.
Well, no, it's one that can't be expressed in a ratio of p over q, where q does not equal 0.
P over q. How is that not the same as saying a fraction? Is p over q not
pi over 1, pi over 2, pi over 3? Those are fractions. It's a ratio. You have a ratio of p or q. That makes something, for example, 0.99 repeating is a rational number. I can express it in the form of a fraction, 1 over 1. You can't express pi in the form of a fraction.
Oh, okay. I do see what you're saying. Yeah. Okay. Well. Okay. Yeah. Sure. I forget what point are you trying to make with regards to?
I'm pointing out that these are real numbers. They're rational numbers. 0.99 is rational. I can actually say 1 divided by 1 equals 0.9 repeating. And I could use calculus here like I did in the group chat to show you why the limit is what it is by definitions. And
Well,
if you're
you never went through with that fully. I mean, I'm still stating that you got there by saying, well, if I just continuously take essentially 9 over 10 some infinite amount of times, then I'll end up arriving at this number of 0.999999999, right?
right.
Which is equivalent to 1. But what I'm saying is that doesn't make sense because, like, you can't ever get there, right? You can't ever arrive at
That's your okay. That's where you make the conceptual error. 0.99 repeating has already arrived. It's already there. The number's complete. That is a complete number. It's not doing anything. It's not going through any motion. It's not magically moving anywhere. It is a complete. It is the termination of an infinite summation that gave you 0.9 repeating. That's the final number. That happens to equal 1. If I have a sequence, okay, let me tell you what a sequence is. 0.9, 0.09, 0.009, 0.00009, etc., etc. That's a sequence, not a series, but a sequence. That sequence, because I'm taking the tenths place, the hundredths place, the thousandth place, and I continue on, the limit of that sequence is defined to be what the sequence converges upon. That sequence happens to converge on 0.99 repeating. Okay? That's a fact. Now, if I take the limit of that, I get 1. They're the same number because of that, because of what I put in the group chat there. Because the limit of 0.99 repeating as k approaches infinity, summation n divided by 10, raised to the n 1 to k is equal to 1. So if I take the sequence, I get 0.99 repeating. I take the limit of that, I get 1. But 0.99 is already the number. It's already completed. It's that equal to, that whole limit. It's equal to all that stuff that I put in calculus. That's what it's equal to.
Yeah, okay, but like if we walk through the steps of how you got there to begin with, you got there by doing what? You say, okay, well, if I do this one time, then I'll get 0.9. If I do this a second time, I'll get 0.99. And if I keep doing this to infinity, right, I'll get 0.999999. And what I'm saying, right, is what the limit is describing is what you're approaching. It's not describing like that there's any point at which you arrive at 0.999999 to allow for 0.999 to be a number.
But if that was true, then we could never take limits of a function to get the slope of that function at that point. But we can take the limit at the function, at the point of the function, to get the exact tangent line on some arbitrary point on a function, because we are getting the value of the slope at that exact point, right? So what you're saying, if what we were saying was true, differential calculus would not even work.
Well, I mean, how so? Are you saying that calculus is like when you take numbers, there's no discrepancy to allow for that tangent? Like I said earlier,
Right, there isn't. Right.
for you to have that line, right? If the points are on the exact same position, aka if they're the same point, then you no longer have a line and you break the conceptualization of
No, no, that's not. Have you taken calculus?
I know calc a little bit.
Do you know? Do you know what first principles are?
Uh,
The formula for figuring out a derivative by definition for limit as delta x approaches 0 or h approaches 0, f of x plus h minus f of x over h.
you're gonna have to slow down if you want me to
Here,
like
actually, here.
conceptualize what you're saying.
I just
Because
did a hangout on this.
because even if I understand what you're saying, you spitting it out like verbally is I'm not going to catch it.
Okay, the very first way to do derivatives is usually by principle what called graphical calculus. Okay, I learned graphical before I even did analytical. The first principle takes a formula, which is a limit that you take, where you take a function, okay, and you add a certain h to it, which is a position on the x-axis. So it's f quantity x plus h. So it's some function plus h minus the original function, which is f of x, over h, the distance you took, okay? When you take that limit, when you do the math as h approaches 0 or delta x approaches 0, you're actually getting closer and closer arbitrarily to some specific point that's on the function until you actually reach a point where you're exactly tangential on the function itself, giving you the slope of a tangent line on any point of the function. That slope is known as the derivative. So if I say, what's the derivative of x squared? Do you know what the derivative of x squared is? Happen to know?
2x, right?
Okay, it's 2x.
Wait, was I right about that? I've done it.
Yeah, no, it's good. No, I got a guy claiming to be an engineer. He didn't even know that. So yeah, that's good. So it's 2x, right?
How can you be an engineer and not know?
Oh, dude, we don't know. It's weird. The guy claims to be a civil engineer. He didn't know what Hooke's law was. He didn't know what Young's modulus was. He didn't know what Pythagorean's theorem was. Yeah. So let's just go with that, right?
Okay.
But anyways, so the derivative that we're talking about is giving us the time rate of change at a very specific point, the instantaneous time rate of change on the function, right? So we can actually say, okay, I know x squared. I know the derivative is 2 of x. And I can do that with calculus, right? You can do the power rule, right? You drop the exponent down, make it the coefficient, drop 1 for the exponent. So basically it's 2x to the first, which is 2x. I got that. But you can actually get 2x by using this other procedure, this first principle procedure.
I mean, you haven't written it out, but I think the procedure you're talking about, you take your function or whatever, and you plug something in, and then the denominator cancels out with something in the numerator, and then you end up getting some final result. But
sort of. I mean, they do cancel, but what happens is actually the delta h falls out, kind of in a way. But when you're doing this procedure and you're taking the derivative of something, you're just basically taking 2 points called the secant, and you're arbitrarily putting them closer together. You're just saying, okay, I have a P, I have a Q point. As Q approaches P, what does it converge it upon? And what it converges upon is that limit. And that at that point is what we're trying to find the limit to be, because that's the point of change we want to find, the tangent on that point. So the same thing happening here.
Might I ask, okay, so if you're approaching a point, right, and you end up having a bunch of essentially changes within the y-axis as you approach it, right? Such that it's difficult as you approach that number to determine like what number you're actually approaching.
That'd be G. The difference in y is called your G, and your difference in x is called your H, or your rise over run, they call it. I should have sent you my hangout on first principles, because I literally just did this as something in the great debate community to show people how this is done using the first principles, but it might have helped. But I think your conceptual error is just that, first of all, you got to understand this is math, and math isn't up for debate. This is a fact. 1 = 0.9 repeating is a mathematical truism. Any college in the world will tell you this. Any mathematician will tell you this. It's not something we're actually debating. It is a fact of reality. But there are some misconceptions that I've seen people have with this, and I think that I'm noticing with you as well, that you're thinking 0.99 repeating is some ongoing process.
Well,
And it's not.
I don't know what I don't think that you can arrive at. I'm just saying that we can conceptualize it as like if you want to conceptualize the idea of 0.99 repeating, the only way you can conceptualize that is through the process of continuously approaching something.
Yeah. And by the way, N.J. Wildberger is wrong. Rob Hartwood, I know who he is. I actually have mathematicians that know him as well. He's a finance constructionist. And he doesn't, I know this very well. N.J. Wildberger does not disagree that within the reals, that 0.99 repeating goes 1. He just doesn't like the fact that there's infinite decimal expansions in it, and he's formulated a different method, a different type of construct, whether you don't have to deal with that anymore. So yes, Rob, he doesn't actually say that 0.99 repeating is not 1 for the reals, because that is a mathematical fact. He's just changes his system because he's a constructionist to where you don't have that problem anymore because he's dealing with finitism. But nice try, Rob. Sorry, Joseph. I'm so familiar with this topic. It's ridiculous. This is the whole topic that got me into YouTube. So
yeah. Okay. So tell me, it's been a bit.
He does. What's like Rob Hartwood, N.J. Wildberger does not disagree with me. I know people that know him. He actually has said that 0.9 repeating is equal to 1 in the reals. He's not disagreeing with me. So trust me on this one. I can get him on here if you like. Go ahead. Sorry. I love it when people think they try to correct something, but something they just out of the blue found on YouTube when they know nothing about it, right? It's amazing. Go ahead. I'm sorry, Joseph. You're fine.
My understanding of the derivative and the way you get that, well, get the tangent line for it, right? Okay, so you take two different, you basically conceptually or geometrically, you can conceptualize it as you have one point and then you have another point, and you're bringing that one point like infinitely close to the other point.
Yes.
Such that you end up arriving at a tangent line. But those 2 points cannot be the same, otherwise you don't have a line. So it has to be infinitely close without.
Well, that's why you take the limit, though. The limit takes it at that point. You don't have a line anymore, but you do have a convergence. All this is about convergence. Where does the sequence converge upon? It converges upon 0.9 repeating. And so where does the line for the tangent line converge upon? It converges on point P. So if I'm trying to figure out the derivative of some line that's on a tangent of the function, it actually is taking it at point P. If not, you wouldn't get 2x. You don't get some weird number like point whatever. For x squared, it is equal to 2x because it is exactly what the tangent line would give you. Think of the tangent line of 0.9 repeating. 0.9 repeating is the exact tangent line of a slope of 1. It doesn't matter. If I have a line and has a slope of 1, it could either be 1 or 0.9 repeating. It's the same number.
Sure, but I'm just saying, like, if you end up insisting that where that tangent line, the second point for that tangent line is on the exact same point as the original point, then you no longer have a line. Like,
well, yeah, but at that point you don't need the line anymore. You converged. So I'm saying you've converged at that point on P, and that's the point you're taking. As it approaches, we're trying to figure out what happens at that point. And so we can do that, and then it all kind of factors out when you actually do the math using first principles. But you can prove that x squared is equal to 2x using that graphical representation. In fact, I think I did that on my Hangout, if I remember correctly. I think it was x squared I did.
That's pretty
But it's
easy.
on the other channel. But again, though, when you're working with mathematical proofs, I mean, you've seen the proofs, right? You've seen the algebra proof for this, right? Obviously.
Probably at some point.
It started with, as I said, Euler actually developed the first one. But you basically start off with 0.99 repeating. You times it by 10. You subtract the 0.99 repeating from both sides. You're left with n equals 1. Have you seen that?
Sorry, I was reading something
Okay, this proof looks like this. I'll type it in the side. You start off with n equals 0.9 and repeating. Okay. Now
Yeah.
you take 10. You times each side by 10. So on the left hand side you end up with 10n, and you end up with the right hand side you end up with 9.99 repeating.
Oh yeah,
Okay.
that's the one that I heard did.
Yeah, and then you subtract 10n minus 1n, and on the other side you actually subtract the numerical value, so 0.99 repeating minus 0.99 repeating, and you end up with 9n equals 9, which means n has to equal to 1.
Yeah, but the problem with that is that might be a proof that 0.999 repeating equals 1 if you already accept 0.999 repeating as a number. That doesn't really.
Yeah, I grant you that. That's why I was like, well, I'm not going to show you proofs. If you don't have a substitute, it's a number. I don't even know where to go with that because, of course, it's a number.
Well, it's been quite some time since I've done anything with calculus, so trying to quite remember how exactly the definition of a limit works and exactly what's going on there, it's kind of hard for me to build to say like converse. I'm looking at the wiki page on some of the things with regards to limits.
Okay.
And how you get the derivative, but I think this might be the formula you were referring to, f, and then in the parameter for f, it's a plus h minus f of a over h.
Yeah, that's the first principle formula. Yeah. And you can actually use that to determine a derivative, right? But this is a little bit different here. We're not actually taking a derivative. I'm just showing you conceptually that the tangent line at that point, because we're taking a limit, actually is at that point. Here we're taking a limit. We're taking a limit of a sequence. We're taking the limit of the sequence of 0.9, 0.09, 0.009, or of the series. A series would be 0.9, 0.99, 0.999, 0.9999, etc. There's a difference. Can you see the difference between a series and a sequence? A sequence would be 0.9, then 0.09, and then 0.0009, right? So you're only kind of showing 19. You're just moving it, back one because of the zeros. But
Yeah.
a series is literally 0.9, 0.99, 0.999, 0.9999, etc. Right? So that's a series versus a sequence. They're related to each other, obviously, but people have asked me, talk more about 0.333 equals 1/3 and it being a number, but 0.99 equals 1 is not. Yeah, no, I did try to ask him that, Barney. Yeah, I still don't understand. If you think that 0.3 repeating, 0.33 repeating is a number, and that is equal to 1/3, and you can visualize 1/3 being a finite amount, right? 1/3 of a pie. You have 3/3 as a whole. And if you're willing to concede that 0.33 repeating is an actual number, you just take 3 of those, you get 0.99 repeating. Simple as that.
Well, I mean, you brought up multiplication, and I told you it doesn't make sense to me because the way in which you arrive at the answer, you don't take and you multiply the numbers out. Or what you were saying is, well, you just do it all at once. But I guess my issue there is it's you can't really do that all at once. The operations for these things have to be one at a time. I mean,
no, they don't. That's the whole point of doing calculus. We can do an infinite amount of steps. We don't have to do each steps. And by the way, Rob, no, he's not. He doesn't. Rob says he doesn't believe in the reals. This guy, other mathematician guy. No, he doesn't accept irrationals. He accepts reals. Reals are 1, 2, 3, 4, 5. Those are real numbers, right? Irrational numbers he doesn't accept, which would be most numbers are going to be irrational, right? They can't be expressed in a form of a fraction. Square root of -2, or excuse me, the square root of 2 is irrational. Pi is irrational. R.J. Wildberger, he's a constructionist, and he doesn't like to have any irrationals, but he certainly has reals. And in our mathematics that we use universally, this holds true. 1 equals 0.9 repeating equals true. He recognizes that, but he has a system that he uses where you don't have that problem. You don't deal with irrational numbers either. But he's a finitist, like I said. He's a mathematical constructionist. Has nothing to do with the topic here, though. Really, sorry. If Rob says, hang on, Rob says reals includes transcendentals, yes, and he doesn't accept reals. So what does he have then? If he doesn't accept reals, what's left? Even Joseph might know. Joseph, you get rid of the reals. What other sets do you have?
You have complex numbers.
Okay, and then what else? Anything else you can think of?
There's like those fucking
surreals, hyperreals.
Yeah, shit like that.
Yeah. So how does he not? How he's claiming this mathematician doesn't use reals? So he's only working in the complex plane or the surreals and the hyperreals. Come on. Yeah. This is what happens when somebody goes look at a video. They have no idea what the hell is going on, right? Yeah.
I'm looking at a case scenario now of what. Yeah, this is what I remember. They take the f of a plus h minus
f of x of h.
Yeah. They plug in and then they factor out an h, and then the h's cancel in the denominator such that they get a final answer.
Yeah, I remember. So the things cancel out. Yeah, I mean, I like I said, I just did a video on it. And Rob, I don't really care. Just for arguendo, so I can shut this guy up. If one mathematician out there that disagrees, who gives a fuck? Okay, one person is nothing. 99.99999, not point, whatever. But the vast majority of mathematicians really.
I'm not even reading what you're talking about. Is it the?
That's live chat. Sorry.
Nestling guy 20?
No. It's this guy Rob who's just talking out his ass. But
Rob.
Yeah.
Okay, I'm looking for Rob.
This is a mathematical fact. There are no mathematicians that disagree with this. None. Not even Weilberger.
Can you point to him accepting the reals? Well, I mean, yeah, I don't know. Like, I don't think most mathematicians would be like make a statement that, oh, I accept the reals. Like, you're asking.
You know how I know he accepts reals? Because every time I've looked at one of his videos, he uses numbers. 1, 2, 3. Those are reals. So you go to any one of his videos, you can see he uses real numbers. And yes, real numbers are complex numbers. Yes. Where I equals 0. That is true, Alan. Yes. We went over that the other day too, trying to explain why reals are a subset of the complex. Because complex are in the form of a plus bi. When you just take I equals 0, that gets rid of bi. You're left with a, so you're just left with the real portion of the complex number, right? So.
Anyway, I'm taking. So they take the function. They take it as it approaches 0 for h, and then.
Yeah, no. If you want, not right now, but I mean later on, maybe in off air or whatever. I mean, if you want to watch my video where I did a presentation on it, I can walk you through how to do first principle to figure out how to take a derivative of something. The reason we don't utilize it is because it's very unwieldy.
Well, from the looks of it, you take your formula, right? F of, and maybe the variables as having the free variables as having different names, but a plus h minus f of a over h, right? You take that formula. You can take the limit as it approaches whatever you're looking for, and then at some value for f, you plug, well, f being the function that we're referring to, you plug in those numbers, and then you end up getting that limit as it approaches whatever number you're referring to for that of h being whatever the number.
Yeah, then as h approaches 0, you can those things go to 0. And you
yeah.
See right.
Yeah, and then in the end, basically, right, your h would drop out, and you'd be just left with some exact number, right?
Right, and that's why we're looking exactly at that point, right? Once those h's go to 0, and you can cancel out each term that has an h in it, then whatever's left over that doesn't have an h in it, like the 2x, that's where you're at that point, because you've eliminated the small arbitrary distances that you put in there, right? Because all you're doing is you're sticking an arbitrary thing and saying, okay, I'm just saying, here's a distance from x, right? And as I decrease that distance to x, what does it approach? That's all you're doing.
Is h the distance?
H is the distance on the x-axis.
Okay, so it would be the distance between the 2 points, and you're saying as h approaches essentially 0, or as it zeroes out, so that the points become infinitely close to one another. What do you get?
Right, because remember, there are no infinitesimals for the reals, right? There are things like you can talk about in the higher maths that even I don't even get into, what's called neighborhoods, where you're so close to something but you're not there yet. But that doesn't exist in the reals. The concepts are there in certain types of other types of maths, but in the reals, there's no highest number next to one that's not 1. Right? If I say what's the highest number that you can think of that's close to 1 that's not 1, that doesn't exist. There's no such number. Because any time you can take two numbers, like for example, x equals 1, and let's say you have x equals 1 and y equals 0.9 and repeating. There's something called a trichotomy property where you can take those two numbers, add them together, and divide by 2. So the trichotomy property states that x is either less than y, x is greater than y, or x is equal to y. If they're not equal, if 1 and 0.99 repeating are not equal, then there exists between them x plus y divided by 2. Because there's no x plus y divided by 2, if x equals 1 and y equals 0.9 and repeating, they have to be the same number, or you violate the trichotomy principle or property. Does that make sense? Did the outside chat get that? Do they know what trichotomy is? It's basically, we just repeat it again. All it's saying is that the trichotomy is that if you have two numbers, they can either be one of three things. They can be equal to each other, x can be higher than y, or y can be higher than x. That's it. Those are your three options. Could you agree there's really no other things you can have?
Yeah.
Okay. If 1 is not equal to 0.199 repeating, then that states that for the rationals, you can add those two numbers together and divide by 2 and get a new number. But you can't do that with 1 equals 0.99 repeating and get a new number. If you there's no number in between them. They are equal to each other. If we want, it's basically saying 1 plus 1 divided by 1, or just to be divided by 2 is 1. You're not getting a new number out of it. You're getting the same number. 1 plus 1 divided by 2 is 1. Same thing here. 1 plus 0.99 repeating divided by 2 is 1. So, I mean, these things have to work out.
I take. So what is your original formula?
I'm just giving you reasons why these things work out the way they do. I mean, I understand you don't think 0.9 is a real number, but that's just something I can't really get around. If you want to think that, that's fine, but that doesn't make any sense. It's a very real number, and if you look into Cauchy sequence, you can actually construct it. Like I said, I just don't remember how to do it because I don't remember Cauchy very well.
I'm trying to look at limits now to see if I understand better what you're saying. Like I kind of see what. I don't know how they derived the formula to begin with, which might be important. Let me go back up. There's.
Well, mind if I take a straw poll real quick? Of how many people think? Okay, in the live chat, I'm just kind of curious. How many people think 1.99 repeating is true, and how many people think it's false?
Oh, I think the majority of people would say like they're equivalent.
I'm just curious. I don't know. This guy's really weird. He's saying this guy does not believe in the reals. What does that even mean, not believe in the reals?
Well,
I don't even know how to interpret that or parse that out. The real number line doesn't exist?
Maybe he only believes in complex numbers. Does everything in complex.
But reals are complex. Yeah, overwhelmingly true, yeah. I haven't seen any false yet. So, like I said, there's a reason, and here's what I want you to take away. I mean, we'll go on a little bit longer, but I want you to take away this. if the entire world is telling you you're wrong on something that's mathematical, including every mathematician that's ever studied this, you might want to take pause and think that's maybe you with the conceptual error, right?
Uh, well, I think you should always take a pause and think about that. So I don't know if that's necessarily a reason to. Uh, it's been forever though since I've done anything with calculus, so it's difficult to converse as to exactly how limits work. You might be correct, but from what I remember, there's still. It's weird to me because I recall like you take and you're trying to get that tangent line, but um from what I recall, like that tangent line is a number so close that it doesn't make a difference. But you're not saying that I guess when you end up arriving there, you don't have the tangent line at all.
Well, you do have a tangent line when you arrive there. That's
Well,
how you
okay,
get the slope. That's how you get the slope of the function.
yeah, but isn't the slope supposed to represent the rate of change at that point?
Yes.
Okay, well, isn't the tangent line supposed to represent the point at um? Oh, sorry, represent. I guess I already asked that. I guess my question is, and you still have to accept though that that tangent line has to have 2 points for it to be a line.
No. The line itself has 2 points, yes, but we're only asking where does that tangent point intersect with the function? Only at one point, right? It doesn't touch the function on 2 points. It only touches it on one point.
Yeah, sure, but there's somewhere else on the function for it to actually be said tangent line. It has to have that point and some other point, right?
The
But like
line has
if
2 points. The line has 2 points, right? Because every line can be defined by two more points. But the point where it intersects with the function, that's all we care about.
well, that can't be true because you're saying that that tangent line itself happens to be representative of the rate of change for at
At
that
that
point,
point.
right?
Yeah, exactly. Exactly. The slope of that line that has touched the function at that particular point represents the instantaneous change at that point.
Right, but doesn't that vary depending as to where the other point is, right? So if
No, there's only one point.
no, but that for the tangent line, I mean, the tangent line obviously has to have 2 points,
But
right?
that doesn't matter. We're talking about the point of where it intercepts the function at. That's only a single point. That point is P, we'll call it.
Yeah, but uh, you're not understanding what I'm saying. What I'm saying is, um, to get this tangent line, right? I know you're going to disagree with this for a moment, right? But um, if you get like the idea is to have that tangent line be as close as possible, right? To the other, have those 2 points be as close as possible, such that you get the line. But I guess my question is, right? How is that possible? You can't have them obviously.
Where the 2 point, okay, where the 2 points converge, right? You have 2 points that your initial secant line, then you have a new one, then you have a new one, and then as Q comes down the function, it's closer to P, where they intercept the point where P becomes Q. That's where we're taking it from. Where the point becomes indistinguishable from Q, they become the same point. That's why I want to get the tangent line.
But then you can't get a line. I don't.
Yeah, you can. You're confusing the 2 points required to take the line to the 2 points that actually the line is producing from the tangent line. You're conceptually confusing two different things here. I wish you would have watched my thing because I had us all. I did this all in a graphing program, and I don't remember what equations I used. I had it all on a table and the whole nine yards.
I mean, you're welcome to link the video.
Yeah, let me link the video because one sec. Yeah, Rob Harford. I don't care, to be honest with you. I don't care. NJ, I know who he is. We've had people that dealt with him. He's a fringe mathematician. He's a constructionist. Has nothing to do with the topic we're talking about. If you go to any college in the world, and learn mathematics, the first thing you have to do in calculus or in the reals is prove that this is true. The first thing. He's not going to change that. Okay. Rob, what NJ is talking about is a different approach using a constructionist approach, which is perfectly fine. He's not wrong, but he's not talking about the math that everybody else uses. Simple as that. So, all right, let me get this green. Let me find this video. Anybody remember what the hell I called it? Introduction to limits and continuous functions. Is that what it is? It's that one. I gotta watch this little video to make sure this is the right one. Do I do this in? Yeah, no, well, this is the first principle one, but it's a good one to watch.
I guess what you're saying, as far as I can tell, is that yes, it has 2 points, but its second point isn't on the function.
Yeah, it has 2 points, but the 2 points that are defined in the line can be anywhere in that line. But the point on the function is irrelevant. I mean, that's all we want to know is that point on the function that we want to know how fast that function is changing. And by taking a slope there to taking a tangent line, we can tell how fast that is changing there. But where the 2 points are that we use to define the line for the tangent line, it doesn't matter. You can use any 2 points, right? Because there's actually 3 points you're dealing with. 2 points that are defining the line, and then 1 point to the P where it's actually on the function. Damn it, I don't even remember the hell I called this damn hangout. I'm trying to remember. Okay, this is Taylor series. Linear equations, continuous functions, first principles. Right here.
Okay, I get what's.
By the way, I totally screwed up the delta. I mean, the epsilon delta on the first hangout, totally screwed that up. Don't just ignore that part. I was so wrong. It's been so many years since I've done epsilon delta, but that's okay. Mathematician got it. Made mistakes in it too, so whatever.
Calc 1 first principles, the delta method. Oh, yeah. Okay. I've looked up some things such that I have a better idea as to what's going on. I can understand why the you can have 2 points for the line, but both of those points aren't actually on the function. Hence, you don't break the principle of a line but still have the rate of change for that point on that function. Okay, right. I get that. Right. How exactly this tie back into 0.9 repeating?
Sure, because if what you were saying was true about limits, we could never get the exact derivative of a function. If I want to know the derivative of x squared, I couldn't get 2x out of it using limits, but I do get 2x out of it. It's an exact number. It's exact derivative of the time rate of change for that function. And then if I want to evaluate it at a specific point, I can do that as well. So when it comes to 0.9 and repeating, the limit that we're taking, it's done all at once. The sequence, if I say what's the limit of the sequence of 0.9, 0.09, 0.09, the limit of that sequence is 0.99 repeating. Okay? And that 0.9 repeating, I can say, is defined to be the limit as k approaches infinity, summation, and that formula.
I don't get where you go from the leap between saying that you can't have the you can't essentially find derivatives if you don't have 0.99 repeating equaling.
No, that's not my argument. What I'm saying is, if limits didn't work the way they did, we never would be able to take a proper derivative.
Sure, but still, I mean, even within the limit itself, you're still saying, like, as you approach this number, what happens? And if I infinitely get close to this thing, essentially,
a limit tells you. But Joseph, a limit tells you what's happening at that point. The method you use to get there.
No, I agree with that.
Okay. So the limit tells you what's happening at that point.
Yeah.
Okay. So If the limit is telling you what's happening at that point, when you take the limit of the sequence for 0.9 repeating, it's telling you what's happening when you add all those things together.
You
It
mean
adds.
when you take the limit of this
Well,
system where the 9 increases and you take to the power 10 or whatever.
Well, yeah, you actually take the limit of the summation of n divided by 10 raised to the n, where n is going from 1 to infinity.
Yeah, when you take that thing, you're saying, well, in the end, if I conceptualize what's happening at every step of the way, I end up getting point. If I just conceptualize that to infinity, I end up getting more or less 0. Sorry, not 0. 0.999999999. Sure, but and so I guess what you're arguing is you have to quote unquote arrive or whatever. Otherwise, you would never have the numbers drop out and you'd be able to get that exact tangent line. And hence,
Yeah, exactly. Yeah, exactly. You'd never get the exact tangent line. But let me show you something real quick. I'm presenting. Can you see my Wolfram Alpha?
Yeah.
So I gotta make it bigger.
Yeah, I can barely see it. I see some limit and then the summation of something.
All right. This is the formula that I typed in the group chat. Okay. The reason why it evaluates is true. Let me show you. What this is saying, okay, this is my formula, right? N divided by 10. Or excuse me, 9 divided by 10. As the n, which is your natural number, right, is increasing from 1 to k as k approaches infinity. So as I take in the limit, right, of this summation, as 1 is increasing each time. So the first time n is 1, 9 divided by 10 to the first power is 0.9. N equals 2 is going to be 0.09, 0.009, etc. That limit will give me 0.9 repeating, which is this. Okay. That also happens to be the exact same thing that equals 1. And I don't know if you type this, but we'll see here. Yeah. So 0.99 repeating is this equal to this, but all this is actually equal to this too. These three things are exactly the same way of expressing the exact same thing. This expresses it as a terminating decimal, right? This expresses is in the form of a limit of a sequence, and this is this is showing it as a repeating decimal. These all mean the exact same value. If I said, "Hey Joseph, point on that number line where 1 is," you could do it. If I say point where 0.99 repeating is, you wouldn't even have to move anywhere. It's the same exact place. They're just representations of different ways of expressing a specific point on the real number line. That's it.
I guess what I'm trying to say though is like, why do you get to say though? Like we do agree still, I think, that the limit is essentially like the number you get out is a definition of some number that you're approaching given some formula, right?
Okay.
So with that in mind, right, I guess back to what I was saying way earlier originally in this conversation, like wouldn't it make more sense to like conceptualize it as the actual number that you're approaching, which is 1, rather than, because we understand that if you take 0.99999 repeating, that is and continue at continuum to infinity, which is essentially what the limit is a definition of. That thing is stating that it's approaching 1, not that it's approaching 0.9999 repeating.
Right, but again, what you're missing is by definition that what I showed you this right. What I showed you that formula is definitional. It means when you have a repeating decimal, that calculus thing that I showed you is the definition given for what that symbology means. So if you see 0.9 repeating, you can stick in that calculus thing that I showed you and get and mean the same exact thing. They're absolutely equivalent. Okay. So again, you're fixated so much on this. Oh, you're approaching 1. You're approaching 1. No, you've already done the math. You've already taken the limit. You've already done the adding of all the this sequence. And by the way, it would help if you had actually taken calculus because you actually learn what's called a partial sums, the limit of partial sums. And those really kind of help conceptualize what something's converging upon by taking the limit of the partial sums. I'm trying to do something in Wolfram right now. It's not working too well. It's kind of working, but let me see if I can do it this way. If you have this, screen share again. Okay, here I have a summation, very simple summation: 1/2 plus 1/4 plus 1/8 plus dot dot dot. Okay, look how it interprets it. 1. Okay, and this is the infinite sum formula that you can use, because if you stick a 1 into here and then 2 and 3, you'll actually get 1/2. Then the second time you'll get 1/4. The third time you get 1/8 and 1/16, 132, etc. So this is the formula that generates this series. When you add all these up to infinity, they converge upon 1. They are equal to 1. So you're adding them all together, but I don't have to sit there and add these things together. I can take 3 terms. That's all it takes. 3 terms to know the series, right? I can add more here.
I think it makes sense to say it doesn't, like, I guess what I'm trying to say is I think it makes more sense to say that instead of saying it equals 1, what you're saying is it's approaching 1. Like, it doesn't make sense to me to say that it is equivalent to 1, because you can never finish it.
But it is 1. You are finishing it. You're terminating. You're adding these together.
How can you terminate in something that is infinite?
Because it's an infinite process that's done by a summation. That's how we got around Zeno's paradox. If Zeno fired an arrow, right, or fired it toward his target, at some point in time, it's half the distance to the goal, half the distance to the target, and then another point is half the distance between that. Another point is half the distance between that. But eventually, the target is reached. The arrow actually does hit the target, right? Because when you take an infinite summation, you actually terminate. It's called a convergence. This series here converges upon 1. It is equal by definition to be 1. It's the same thing as saying 1.
Well,
so I can add all these
that paradox could be explained simply through the fact that, like, if things have like very discrete amounts to them, such that you have to travel only a certain amount within, like, if time and space have discrete limits to them, that could explain the paradox rather than having like infinite like summations of things.
Well, I don't know why you think that you can't do an infinite summation in a finite time. That's why we have infinite summations.
Well, I don't think that you could. I don't think it makes sense to say that you can ever do an infinite summation of something.
You could, what, again, if I know I'm adding 1/2 plus 1/4 plus 1/8, if I know that's my series, I could just say, okay, what happens when you add up all these numbers together? You get 1.
Well, that doesn't make sense to me. I would say that you could say that, well, because it's impossible to add up an infinite number of things, because the notion of addition is like an operation, and to do an infinite number of operations takes like an infinite amount of time.
No, that's why we have summations. Summation's not required any time to do it. The only time it takes is for you to figure out in your head what it is, or use a computer program. But you're not actually adding all these things together. You're not saying, okay, I'm going to take 1/2 and then I'm going to write it down. I'm going to add 1/4 to it. I'm going to write it down. You don't do any of that. You just say, hey, I look at this series. I know how to do an infinite summation of it. Boom. Here's what it converges upon. It's no time at all.
Sure, but you're taking, like, you're rejecting the fact that you'd have to have operations for each one of those individual parts. And you're saying that this can all be conceptualized in a single operation.
Yeah.
I don't understand why you would say that.
That's calculus. That's how a summation works. That's how a limit works.
Right, but the only reason why we're saying that we can do this is by our already like understood conceptualization of what happens when you take it in smaller, right, like operations. So if I break up that infinite so each one of those parts of that summation, right, the way in which we originally arrived at this conceptualization was through saying, okay, well, I take one operation of this addition, then another one, and another one. But so I would still say that those operations are there that
How,
there
how, how
is
many how many points Joseph, how many points are there on the circumference of a circle?
uh,
Say infinite. It's infinite. How many points are there on a line? Infinite.
sure,
Okay,
but like I understand that lines don't exist outside of math, and nor do circles. Like,
okay, we're talking about Euclidean geometry. Let's assume Euclidean. Okay, if I take a line, right, that's pi length, right, and I make a circle into it like a circumference, right, that's an infinite amount of points. But I can transverse it. I can go around and around as much time as I want. I can add all these points together, an infinite amount of points, and I get something finite out of it. Happens all the time. You calculate all the points on a line or line segment, even it doesn't even matter. Line segment. You add up all those infinite points, you get the line segment. You can do it. You can do it mathematically. You can add infinities all the time.
or you could just say that those, like the line itself, doesn't actually exist. It's only there as a conceptualized
Well,
to
that's
conceptualize the
just
problem.
ridiculous. This is a closed hangout, by the way. I'm not inviting anybody in. Um, yeah, that's just ridiculous. We know line segments exist on
Sure,
Euclidean.
line segments do, but what about that?
Well, lines exist too in Euclidean geometry. They don't exist in non-Euclidean.
Yeah, but like the way in which me and you are conceptualizing lines are very different. I'm conceptualizing as these useful tools to like visualize what happens
A
in a.
line is basically a bidirectional ray. It extends in either direction.
Yeah, I get that, but what
Okay.
I'm saying is, um, it's it's a tool to help conceptualize things like functions, and things like that, or in a sense, we do call them functions, but they don't they don't exist in the sense that there is a moment in which you can have a line.
I'm not following you.
What I'm saying is, it only exists to be able to conceptualize things. It doesn't, like, lines don't actually exist.
Yeah, they do.
Okay, point to a line in reality.
Okay. No. Wait a minute. There's a difference. You just said in reality is Euclidean, right? Or non-Euclidean. I mean, we live in a non-Euclidean universe. I can't point to a line. Um, I can't point to a line in the universe because there's no such thing as a real line in the universe. But in Euclidean math, there's a real line. It's an artificial construct. It's an abstract concept. It doesn't exist in reality.
Well, I would say that I would say its
lines,
inability to exist in reality means that, as outside of it being a useful tool to conceptualize something, it doesn't exist within the math either.
most of math doesn't exist. Numbers don't exist. They're all abstract concepts. So what?
Yeah, but we're using
Two doesn't
exist.
exist.
We're using exist in two different ways now. Like, you're using exist in the sense of like
Concretism. In other words, they don't exist in the reality. They don't exist in form. They don't. I don't believe in Platonic realism.
but I guess what I'm trying to say is it doesn't, like, it, the nature of it having this idea of existing in the sense that it is there in math or in reality is contradictory, because you can't have infinite things.
Right. That's what I'm saying. These are all just constructs. Right. They're just mathematical conceptions. But in Euclidean geometry, you can have a real line. Now, a real line has an infinite amount of points on it. I can add up an infinite amount of points, and I get a real line. I can add up an infinite amount of points. I get a line segment. If I say, okay, if I have a circle with 1 inch, well, I should probably use metric system, but if I have a circle with a 1 inch diameter, what's the circumference?
Sure, but that's not what I'm
It's pi,
saying.
right? So I mean, that's a irrational number, but that's the circumference.
Okay, so what process do you use to quote unquote add up all the points on a line? Because I would say that
Summation.
yeah, but by then I would say that the way in which you're conceptualizing a line is not the way in which you were originally conceptualizing a line, right? So yeah, we draw them as if to say that if I continue this function on, we'll get said line, right? But the problem is you then take that and you say, well, there's a point at which instead of just saying, if I continue on, I'll get the line. You're saying I have the line; it exists as this thing, rather than this thing that I'm conceptualizing as the notion of if I continue it on.
I'm going to try to follow that. A line is a line. You can take any line segment and extend it; it becomes a line in both directions, right?
Yes.
But there's just as many points on a line as there is a line segment. Do you agree with that? There's a one-to-one correspondence. You can do a bijection from any line segment to any other line segment or to any line. There's always a one-to-one correspondence. There's just as many points on a 1-inch line as there are as a line that's 1 light year.
Yeah, I agree on that. What about that?
All right. Because you're so fixated on these infinities that you don't seem to realize that we can add infinities easily. They're not that hard to add and work with.
Well, I mean, even if I take, I would say that it doesn't make sense to say that you can have a summation of all the points on a line segment either.
Why not? If I arbitrarily give each point a value and I say I want to add all these points together, there you go.
Okay, well, what do you get out at the end of that?
The measurement of the exact measurement of the line segment.
What do you mean exact measurement?
Well, I mean, what's the diameter of a 1-inch sphere, or excuse me, 1-inch circle? If it's 1 inch across, the diameter is 1 inch, right? If you draw a line from one side of the sphere to the other, it's 1 inch, right?
Yeah, but I don't understand. You're saying, but diameter is the idea of the length between the two, not what would, I guess, and it's bad to even use this language, but the volume in a sense of the line.
Well, it's one dimensional.
Yeah, I know, that's what I'm saying is bad to even use that term, but I can't think of a better analogy to what's being described here. Like, if you quote unquote add up the summation of the line, you don't get a meaningful result.
If you add up all the points in the line, you get the line segment. You get exactly how long it is. The point being is we can take any amount of something and do an infinite summation in real time. I always thought that was confusing when people think for some reason this requires time to do. No. If I have all these numbers, I can add them up instantaneously if I want to.
No, my issue is not even really with time. It's the fact that it seems like you have an infinite number of operations.
But, well, you kind of do in a way. I mean, you have an infinite amount of addition. If you have like 1/2 plus 1/4 plus 1/8, there's obviously addition binary operators that are between terms, right? But when you're doing a summation, it doesn't matter. You just say, okay, I'm just adding these all together. What do I get? Well, they converge on 1. Therefore, if you add them all together,
yeah, but we're looping back into the conversation I had earlier. And so I say, okay, so how do you exactly define this idea of the single operation? And like I was saying earlier, the only way in which you define that quote unquote single operation is saying, okay, well, what happens if I add one of these things and another one of these things and another one? In other words, the way in which you arrive at this quote unquote one operation is through taking the infinite number of operations.
Yeah, that's what you're doing. You're taking
it's no longer a single operation.
It is a single operation. It's just the single operation is for the summation is a single operation. You're taking an infinite amount of steps and you're doing it one time. It's one operation that it takes into account all those things. So you don't have to do each individual step. It takes into all into your account.
Well, that rejects what the notion of a single operation is.
No, it doesn't. When I multiply something, that's people think of that as repeated addition, right? If I say 2 times 4 is 8, right? That's the same thing as saying 2 plus 2 plus 2 plus 2, right? But I'm not actually adding these things together. I'm doing a single operation that we're calling multiplication that does the same thing as just adding them together.
Well, we consider that a single operation.
It is, right. It's same with the
no. I mean,
exactly. Thank you.
We don't consider
single operation. Summations are a single operation. Thank you.
No, because depending as.
Oh, come on! You almost have it, Joseph. You almost got it, man. You're right there.
Multiplication is only considered a single operation within certain areas, right? Like if I'm programming in certain languages, right? I don't know about more certain versions of the fuck am I trying to say?
I I don't know, but you're so close. You just recognize that instead of having to add 2 plus 2 plus 2 plus 2 to get 8, I can just do it in a single operation and say 2 times 4.
Right,
Or
but okay. So let's
or I
say
can
I'm
say,
programming with a specific instruction set on computer, right? And so I'm programming in binary, right? For whatever reason, right? There might be different versions of this in which they do it in a single operation, but at least in that form, we wouldn't say that the operation of multiplication is a quote unquote single operation. We would understand it in that context to
okay,
be multiple
don't jump to
operations.
computers because I know about programming too, but you're gonna confuse yourself even more. I don't want to really go down the computers. I'll
No,
just
no, but it's relevant to make my point. The point I'm trying to make is the reason why we consider multiplication to be a single operation when we're referring to like us doing multiplication on like paper or whatever, or in our heads or whatever, is because we're not requiring ourselves to basically do other operations to get there, right? If I multiply 3 by 3, the answer 9 pops out into my head without me doing the addition of 3 times, right? And so it
okay.
becomes what
Let,
would be the ideal of a single operation. You don't really get that same concept when you're referring to the infinite summation.
okay, let me show you something here. This is the same thing. Okay, so I mean, don't send me messages, people. People send me messages. I don't want to like
I
broadcast.
don't even know if it's very useful to consider multiplication to be
Okay,
a
see this right
operation.
here? This is an exponential operation. Okay, 2 raised to the third, right? Right? 2 raised to the third. I don't have to. If I say, "Hey, look it,
I like
I
a bar.
look it, I
Okay.
have 2 plus 2 plus 2 plus 2, and I know I can take an exponentiation and do this. If I had this repeating to infinity, I still have a way of adding those things together, which is summation. This right here, 2 raised to the third, is a single operation that takes into account 2 plus 2 plus 2 plus 2. By doing a summation, it's a single operation that takes into account 1/2 plus 1/4 plus 1/8, etc. These are single operations on this side of the equation that just represent this. That's all it means. So yes, we can do an infinite amount of operations in a single amount. In fact, if I do this, let's see where that actually comes up to. Yeah, here we go. Here, this is what the sum diverges means. It goes up to infinity. But this is how I would represent this series, right, to infinity, right? This is just by this symbol right here.
No, but we already went over why I don't even think it's useful to say that multiplication is a single operation.
Multiplication is a single operation. It's a binary operator. It's one of the most fundamental binary operators in ring theory.
What?
Ring, you know where ring is?
Not
Group
sure.
field. Okay, never mind. We won't go down that route. There's really, when you get into more advanced maths, there's only really 2 types of things that you're going to really be dealing with: addition and multiplication. Because division is defined as a reciprocal function of multiplication, and subtraction is just the inverse of addition. So really, there's only really 2 things that are clearly defined. Division is defined somewhat as far as what's called a partial binary operator, because it doesn't work for 0. But when you're making a ring, you really only need to do it's real analysis. You only need to work with addition and multiplication. But yeah, multiplication is a very real operator. I don't know how you think that it's not. It's a very fundamental operator.
I think that the way in which we use the word operator when like describing multiplication is fine in the sense that it allows us to get by because most people are able to again do it in a single step in their head without requiring to do multiples of something, right? But I don't think it's very useful to describe it that way, and in particular when it comes to computing, there's different instruction sets that like maybe there's more modern instruction sets that are able to do multiplication in like a single step, but I'm not familiar with anything like that.
Well, but see, this is where I didn't want you to get confused. The way a computer does multiplication is different from what we would actually do multiplication in mathematics. Okay, computers don't have the ability to actually do multiplication. What they do is repeated addition.
Yeah.
And they don't even have the ability to subtract. They just add negative numbers. Okay, it's a completely different concept, and it's going to get you confused if you think of it as computer stuff. In mathematics, I don't have any clock CPUs time slices that I need to give to doing a evaluation of something, right? I don't have any finite amount of time that needs to be considered to do an operation. I just say, hey, here's my left hand side. What does it equal
But I'm
symbolically to
not
the right hand?
saying that the problem is because it has a bunch of operations, therefore you can't. We need an infinite amount of time, therefore it can't be done. What I'm saying is the fact that there exists an infinite number of operations doesn't tell you where to begin. Like,
Well, it does. Again, I've explained it that you do know where to begin. You begin at the first decimal place, and you keep going. If I want to add 0.33 repeating, I just say 0.33 repeating plus 0.3 repeating. I just go, okay, the first one, 0.3 plus 0.3 is 0.6, 0.03 plus 0.03 is 0.06, 0.03.
okay, well, fine. Then I'll flip it on you and then say, well, then you don't know where to end.
There is no,
If you know where to begin the quote unquote addition of these
that's why you have those
operations,
three little
then
dots.
you can't then define where you're going to end.
Because it doesn't end. That's why you have those three little dots. It's non terminating. That's the whole point.
Right, then you can't actually get an answer out if it's.
Yes, you can. 0.33 repeating plus 0.33 repeating is 0.66 repeating, and there's my answer. Done.
Well, I went over originally that like the way in which we would do
That's
that
not complicated.
operation.
But it's true, though, right? 0.33 repeating plus 0.3 repeating clearly is 0.66 repeating. Would you not?
Yeah, but not because you're adding up each one of those decimals.
That's exactly what you're doing. That's exactly what you're doing, man. You're adding each decimal place.
No, you convert it into a fraction and then you add those fractions together.
You don't need to convert it into a fraction. I can do everything from decimals.
Well, no, because again, like you're not. You're not. I mean, you're.
Well, I've just demonstrated that I just did 0.33 repeating plus 0.33 repeating is 0.66 repeating. I just did it. Do it in my head. It's easy. Doesn't require converting to fractions. It doesn't require figuring out every single decimal place. That's what the 0.33 dots is. It continues the sequence, right? If I get the first three, 0.33, 0.333, then I already know what the other ones are. I just put dot, dot, dot to represent it, you know?
Yeah, but I mean, then the problem becomes, sure, you understand that these are infinitely repeating, therefore, like, with that knowledge in mind, you end up doing the addition in this way, but I still think it's flawed because you're not actually doing the addition.
Well, I'll tell you, Joseph, again, I'm going to be ending this because I got some other things to do, but it's either you're right and every mathematician in the entire world is wrong, including everywhere that you're ever going to learn this stuff and every college you go to. And if you aren't able to accept this proof and you aren't able to demonstrate that you have a concept of it, you'll fail the class. It's simple as that. They don't have time or the patience to do like 2 hours that I have like trying to help you understand, which I'm grateful for, and I want you to go watch the video I just did on this. But if you ever go to college and you
believe me, you can still do calculus without.
No, you can't. You cannot understand the concepts if you don't understand this. You can't. It's just not possible. If you get in limits of sequences and partial sums, there is no way you can conceptually get that if you disagree with fundamentals. And 1.99999, which means 1.99 repeating, is fundamental. You actually have to prove that to be the case mathematically in like one of the very first things you do.
Well, no, that's not true. I've taken
it is true.
Okay, I've taken.
I have books on this.
I've taken a class on calc, and they never had me.
You did not take a calc. You did not take a course in calc where you've learned sequences and series. It's probably calc level 2 that you did. I'm sure you did not take because none of this seemed very familiar to you.
Taylor series, and shit like that. I don't remember it too well because it's been forever.
I did a presentation on Taylor series as well.
Well, I'm just saying, like it's been a really, really long time, but we did go over series.
Well, then you may have got lucky, but I'll tell you what, to anybody else ever listening to this, anybody else who takes mathematics, this is a fundamental. This is true. 1.99 repeating is an absolute fact. There is no debate on it. There is no controversy. It is a reality. It's taught that way in every mathematics course in the world because it has to be that way for many, many different reasons. We didn't even get into the proofs, right?
I mean, you're not going to really run into that many problems, though, like with the way in which they're going about things. I just think that putting the equal sign there isn't really truthful to what the statement's saying.
I think it's absolutely truthful. It is exactly there. It is no different than saying 1/2 equals 0.5. Those are equivalent things. Absolutely equivalent. Yeah. By the way, I have to differentiate. Most people have to do this if they're going to a mathematics major. If you're an engineering major, they don't give a fuck. Engineers are not that bright. No offense to my engineer friends. No, I'm kidding. No, it's always been a thing between engineers and mathematicians, right? Math engineers don't have to learn math as much as people that actually are majoring in mathematics, and I'm not either. So don't take me as authority by any means. But I have seen that math, the classes you have to take to be a mathematician and the classes you have to take to be an engineer, mathematics is way harder, way harder. But anyways, go ahead and get the final word. Be my guest, because you know I'll give you props, Joseph. I like you already because you actually came in here and you were willing to have a discussion on it. I can't ask for anything more than that. As much as I fundamentally think you're wrong, and we'll continue another time, and you should watch the videos that I had on it. I got to give you a huge amount of credit for coming in here and having a discussion. So.
Oh, thanks. I don't think coming in rooms all that brave, but.
No, well, you'd be surprised, dude. People, I've had people that have never stepped foot in here. Darwin's deity won't come in here. Never stepped foot. True Empiricism, who I had a debate with on ATP synthase and turbines and all that, he's never stepped foot in here. They're cowards, fucking cowards. So
Yeah.
Yeah. But anyways, I do have this to do. So go ahead and give your last word. Be my guest.
Oh yeah, I mean, I think I've said my points already, so I'll just say thanks for coming on and talking.
Awesome. Enjoyable. All right, I look forward to let me know when you watch those other videos on the GDC channel, okay?
Yeah.
All right. Thanks, buddy. All right, thanks for watching, guys. I know there's other stuff going on. I know this is math, so this is going to be one of those things that only a handful of people are going to watch. I get that, right? People talk about math and their heads explode. I might be doing a presentation later on tonight. I don't know. I'm really tired, and I got a lot of people that want to talk to me for some reason today because of the drama going on in the GDC. And I'll try to talk to as many people as I can. But for the most part, I think this is all fabricated drama. I'll listen to people's opinions, but I got to tell you, this is my channel. I run it the way I want. I'm not going to let people tell me what I can and cannot do with it. It's simple as that. If they don't like it, don't watch. I mean, I love everybody who watches my live stream. I love everybody who comes in here. I love all the members of the GDC. But the first person who tells me how to run my channel, they can get the fucked. Okay, so it's simple as that. And if anybody disagrees with that, I'll talk to you about it. But I don't see why somebody else has to tell me how I should run my channel. It's just mind-boggling to me. So because I don't tell anybody else how to run theirs. So, anyways, Joseph, thank you very much, and thanks for watching, guys. Again, sorry, this was a math hangout.